Just before we get started with the first talk, I want to make clear what the plan for the workshop is. If you look at the schedule, which you can find it in the INPA website, or maybe in your little bag if you're registered, you'll find lots of time slots for, well, this morning and this afternoon we have slots for open problems and other slots for working groups. So part of the idea of the workshop is that we all work on problems that are going to be posed here, or maybe other problems that you fancy, and hopefully with the people around you. So we think that's an important, maybe the most important aspect of the workshop. Of course, we also happy to have an excellent list of speakers. And perhaps I'll introduce the first of them, which is Joel Spencer from New York University. And he'll be talking about preferential attachment when stable.
Okay. Obrigado. It's really a pleasure to be back in Rio and at INPA. And, well, this is a workshop, so rather than giving a general talk about probabilistic methods, I want to give a problem that I'm currently working on with Svante Janssen in Uppsala and Subabrata Sen, who's at both MIT and Microsoft New England. Okay. And so I'm going to look at a balls into bins model that's called preferential attachment. There are many generalizations, but I'm only going to look at 2 bins. And I start with 1 ball in each bin. And then the balls come sequentially. But this is preferential attachment. The phrase I like is the rich get richer. So when the ball comes, it looks at how many are in the 2 bins. And it has a preference toward the bin that already has more. So you can see Microsoft and Apple are fighting for customers, but whoever has more customers, the next customer is more likely to go with them. And in this case, it goes with the alphth power. So if there are A balls in one bin and B balls in the other, it goes into the bins in proportion to the alphth power. Now, if alpha equals 1, this is very well studied. This is called the Polya-Ern model. But we're going to look at the case where alpha is greater than 1. So there's, and it's quite a bit different. And so this is, you might call it super preferential attachment. And we'll define the term bingo of Mn means that when you're doing this, you reach the place where the first bin has M and the second bin has N. Notice there's no going backward, so you either hit it or you don't. Okay. So equally well, it could be a Markov chain. That's what I put over there. You can have a Markov chain. The state AB means you have A balls in the first bin and B balls in the second bin. And that's the state AB. And then you go from AB to A plus 1B with those probabilities. So those are exactly the same. And it's helpful to be able to go backwards and forwards. But the key idea in analyzing preferential attachment is to use continuous time. And continuous time, well, I said I wouldn't make general comments, but I am going to make a general comment. Continuous time is just a very, very powerful tool in analyzing discrete processes. Here, the continuous time, we start at time 0 with 1 ball in each bin. And the bins act independently. And when a bin has T balls in it, the amount of time it takes till it gets the next ball is exponential with rate T to the alpha. Exponential with rate kappa, the way I think of it is in infinitesimal time dt, it has probability kappa dt of getting the next ball, but it also has the forgetfulness property, that it doesn't matter that it's been waiting for 10 years, it's still the same amount of time till it gets. So this is the exponential distribution. And if you have two exponential distributions of rates kappa and lambda, the probability that the kappa comes first is kappa over kappa plus lambda. Furthermore, we have the forgetfulness property. And so what happens is this is the same process. It's not asymptotically the same. It's precisely the same. The discrete process is simply a discretization of this continuous time process. So this is extremely powerful. And now here is the book proof that with probability 1, one of the bins will get all but a finite number of the balls, what's called total domination. This is not true in the Polya-Ern model, if you've studied that. But it is true as long as alpha is greater than 1. So once again, the result is with probability 1, one of the bins has only a finite, at the end of the process, one of the bins has only a finite number of balls, and the other has an infinite number of balls. Okay. And the proof is via continuous time. You let x infinity be the amount of time until the first bin gets all of its balls. And y infinity be the same thing for the second bin. Now, x infinity, so they're the sum, x infinity is the sum of independent variables, and its expectation is finite because alpha is greater than 1. The expectation is t to the minus alpha for the t plus first ball. Summation t to the minus alpha is finite. So this process ends in finite time. So both processes end in finite time. Now, they're continuous time processes. They have continuous distributions. The probability that they end at the same time is 0. And so what happens is one of them ends, and the other one hasn't ended yet. But if the other one hasn't ended yet, it only has a finite number of balls. So this is a proof from the book. So let me diverge a little bit and talk about the book, which is, I think, a wonderful idea of Paul Erdős. But before Paul Erdős came up with the idea, it was a beautiful idea of the great South American writer Jorge Borges. And I just, one of my favorite quotations is from the Library of Babel by Jorge Luis Borges, que el cielo exista, aunque mi lugar sea el infierno. It's such a beautiful, beautiful sentiment. And if, like me, you're not privileged enough to be able to read Borges in the original, I can also give a sigh. I should have put in the Portuguese as well, but I figure between Spanish and English, we're only leaving out the null set here of people. Yes, a wonderful idea. And Erdős, what Borges called El Libro Total, Erdős called the book. And the book has all the theorems of mathematics. And for each theorem, there is one proof. And that's the book proof, the most beautiful proof. And it's a marvelous idea. And once I was introducing Erdős, and I spoke about the book. And very fortunately, I made an error. And I said that the book is held by God. And Erdős never contradicted anybody, but he began his lecture with a beautiful comment. You don't have to believe in God, but you should believe in the book. So for me, these are words to live by. Oh, I have to blank out here. Whoops, too fast. So many of you know Roberto Oliveira as an intelligent, energetic, thoughtful man. But there was a time when he was an intelligent, energetic, thoughtful young man. Now, somehow Bianca is still a young woman. I can't understand this, but and he was my student and wrote a beautiful PhD thesis on preferential attachment. And I've kept on thinking and thinking about these problems. And what I'm talking about today can be thought of as a follow-up on Roberto's beautiful PhD thesis. So besides total domination, let me look at, instead of total domination, mostly I will talk about the probability of hitting the point Mn, though we could equally well talk about total domination. Pretty much think of M equals N, but here is the limit value of the probability of bingo. Think of M equals N, so it's constant N to the minus alpha. And the proof is via continuous time. You wait until the first bin gets M balls, and until the second bin gets N balls, and you look at the time delta between them. Well, there are two cases depending on which one comes first, but they're similar. And then, in order for bingo to occur, it must be that in this case, where x upper m is less than y upper n, then the waiting time till the next ball comes has to be greater than delta. So this is a tautological thing that bingo occurs. There are two cases, depending on whether delta is positive or negative. When delta is positive, so I have it reversed. Actually, this delta is minus delta over here. I have it reversed. So you look at delta, and delta has to be, if it's positive here, so it's x upper m minus y upper n. If it's positive, then the waiting time for the nth ball on the other side has to be bigger than it. Now, the delta mn, in the limit, it's like delta, and delta has a PDF, which has a value, some constant beta at 0. All of this requires some careful proof, and that's why it's really good to have a strong young guy like Subabrata in the group, because he proves it formally. So there's a PF. And now the probability, see, y sub n is going to be very, very small, because its expectation is n to the minus alpha. And so the probability that delta, that y sub n is actually bigger than that is like beta times the expectation of y sub n, which is beta n to the minus alpha. So we get this, this asymptotic result here. Along with total domination, we actually get the asymptotics. You might notice that these sum up to, you can't sum them up over all m and n, because then it would be infinite. But of course, if you hit one point, you'll hit other points. So if you're careful, in fact, you can derive the probability, for example, that both bins get at least n balls, which in fact was one of the elements that was in Roberto's thesis. And you can just derive this from this as by looking at a sum. But we're going to look more at bingo. And so, okay, this was the thing I've been thinking about since 2004, and then in the last 6 months or so, had some progress on it, which was to search for the proof. So we have the book proof. What about the proof that's not in the book? I mean, the probability of bingo, you have all these different paths, and each path has a probability. So you just add up the probabilities, and that gives it. Now, we already have the book proof argument for what it is. How about the proof that's not from the book, just adding up the probabilities of the path? And what happened was, to our surprise, is that it actually worked in reverse. That is, knowing the book proof, we were able to get a very interesting large deviation. And we were also able to say, what is the nature of the path conditional on bingo? So this, again, is a general result. You have a low probability event that you're, again, think of m equals n, that this process, which is highly unstable, is stable up to nn. Given that, what does the process look like? What is the process? Conditional on the very rare event. So here's a general path. I'm just going to go to the point nn. So we look at the path that starts at 1, 1, and we really look at how far it is off from the main diagonal. So p sub I is when the sum of the coordinates is I, and delta I is really how far away it is from the main diagonal. And then the probability of that path at each step, you're multiplying either xi to the alpha or yi to the alpha, and you're dividing by xi to the alpha plus yi to the alpha. But one thing helps us, the numerator, no matter what path you take from 1, 1 to nn, the xi to the alpha, the xi ranges from 1 to n minus 1, and the yi's range from 1 to n minus 1. We don't know in what order, so the product of the numerators is going to be n minus 1 factorial to the 2 alpha, regardless of the path. And so what we're left with is the denominator, which does depend on the path. Okay, so we're still exact here. And now we want to look at this denominator, and we'll split the denominator into a base times a cost. Cost is perhaps not the best word because it's going to be less than 1. So the base is what the probability would be if the ith point was the point I over 2, I over 2. Of course, that can't be if I is odd, but if it were, then in that case, what would happen would be the denominator here would always be twice I over 2 to the alpha, and then you'd be multiplying from I equals 2 to 2n minus 1. So the base would be 2n minus 1 factorial to the alpha, all in the denominator, and then you'd get this power of 2 that you'd get. Okay. But on the other hand, that's times the cost, which is that you're not at the point I over 2, I over 2. So what is the additional cost factor, which is going to be less than 1? You have to be careful of that. And that's given by this term, which is less than 1. So you notice xi plus yi equals I over 2. So that's less than 1. And the cost is just the product of the cost. So we get the base times the cost. And then let's take out a factor of 2n minus 2, choose n minus 1, which is the number of paths, and make it the expectation of the cost over a random excursion going from 1, 1 to nn. And so base, we have a specific thing. This is specific. When we work it out, we could be much more precise with Stirling's formula. We could put in the constants here, but I just give you the result that the probability of bingo is n to this power minus 1 plus alpha over 2, plus smaller order terms, which we could get exactly, times the expectation of the cost. So now the cost, you've got this random path from 1, 1 to n, and the cost is measuring how far you deviate from the main diagonal. The further you deviate from the main diagonal, the smaller the cost. Now here are the asymptotics of the cost. So up to now everything's been exact, but now I will do some asymptotics. If you let epsilon be the ratio delta I over I, then the cost is given by, still exactly by this function of epsilon, so that's still exact. But now we're going to think of epsilon going to 0 and look at the Taylor series for this. And when we do that, we see that the log of epsilon is like minus lambda epsilon squared, where lambda is alpha times alpha minus 1 over 2. That is, the Taylor series for this is 1 minus lambda epsilon squared plus higher order terms. Okay, I mean, you're going to get something. That's what you get. All right, now we're going to hand wave and just think of using this approximation, and then we're just going to multiply all these costs together. So we'll replace the cost by e to the minus lambda epsilon squared, and then what we get is minus lambda, and then we're summing the epsilon squares. So the key thing then becomes this variable L, which is the sum over the excursion of the epsilon squares, that is the sum over the excursion of delta I squared over I squared. It turns out that this is a very interesting random variable. And it turns out that making an excursion, you get the same result if it's a random walk. That's not obvious, but it's true. So if you prefer, you can just think of this as a random walk with steps +1, -1, and you let SI be the position at time I. So we're moving to 0 mean. Instead of going up the diagonal, we're looking at how far off the diagonal we are. So we have a 0 mean. And we have this very interesting random variable L. Summation I equals 1 to n of SI. Oh, I'm sorry, that's SI squared over I squared. My mistake. That's SI squared. Yeah, I think I had it right. Yeah. Okay. So in terms of the mean, the expected value of SI squared is I. So the mean is simply summation of 1 over I, which is like log n, which is like natural log of n. Okay. But we'll be interested in the Laplace transform, or equivalently, we'll be interested in large deviations for capital L. So there are two elements of scaling that are very helpful. We can scale SI by square root of I, so it's like the number of standard deviations off the mean. So we scale SI is square root of I times lambda I, and now lambda I is standard normal asymptotically, and it further helps to scale time to put time on a logarithmic scale. So we have this awkward notation. Lambda of t is what lambda is when I is equal to log t. And then when you do it, L is the sum of lambda I over I, which then becomes the integral up to log n of lambda squared t dt. Now lambda squared t for any particular t, lambda is a standard normal, so the expectation of lambda squared is 1. And so you'd like to say it's like the integral of 1 dt, which is log n. But again, we want large deviations. And the tricky thing, or interesting thing, about this lambda is the correlations. There is correlation when you're close together on the logarithmic scale, That is, if you know the value at e to the t, and now you want to know the value at e to the t plus s. So going back to I, if you know where you are at I, that affects where you are at 10i. But its effect on 1000i is minimal. And in fact, the actual, we can really give it exactly by this formula. I'm sorry, that L should also, that should be also a capital lambda, my mistake. So what happens is you have a local correlation on the logarithmic scale. What happens at I greatly affects what happens at 1.1i, but it has a very small effect on what happens at 100i. What makes this interesting is that normally, like with Brownian motion, you like to scale to the compact interval 0 to 1, but you can't do that here. If you try to scale 0 log n to 0, 1, then every point becomes independent. We tried it. It really doesn't work. You can't further scale from the 0 log n. So it has this interesting difference between this and Brownian motion. And what we want is the large deviation. What is the probability that lambda of t is less than or equal, that lambda, or that L is less than or equal to c log n, where c is a constant less than 1. Okay, so we know the expectation is 1 log n. But here, we were going along on this, trying to get this. And what happened was we really got stuck, and we just turned the whole argument around. So now let's turn this around and say, well, we know from this book proof using continuous time, we know what the probability of bingo is. Therefore, we can use that and turn this thing around and solve for the Laplace transform. And again, these plus little o1s could be made much more precise. So we can actually solve for the Laplace transform, and then we can take the reverse Laplace transform. If we know the Laplace transform, we get the large deviation. And what happens is the probability when c is less than 1, that L is less than c log n is given by e to the minus this number times log n, where this number turns out to have this very nice formula that we don't fully understand why it's so nice, but it is nice. It's 1 minus c squared over 8. And I couldn't find any direct argument to this, but I asked El Mago, the magician, Svante Jansson in Uppsala, and Svante solves all problems. And he did manage to find a direct argument for the large deviation for L, and it's a very subtle argument using eigenvalues. It turns out if you make the step sizes, instead of being plus 1, minus 1, if you let them be IID standard normal, there's some arguments in that case using eigenvalues. And then you have to use an argument that replacing the standard normal by plus minus 1, the result is still the same. So actually, there is a direct argument for the large deviation for L, but it's not a particularly easy argument. And then we can further ask, suppose we do hit NN, what does the path look like? So again, this is like a general problem. We have this rare event that we have an unstable system, but we condition on stability. We condition that it hits NN. And it doesn't have to be exactly NN. We'd get similar results for other conditioning. So conditioning on the fact that it has remained stable this very unstable system, conditional on the fact that it has remained stable, what did the path look like? Does it look like the average path from 1 to nn? And the answer is no. It doesn't. Well, it looks like it, except there's some change. There's some similarity, but there are critical differences as well. And it turns out that the answer is a well-known process, which I had never heard of, but again, I've got two probabilists in the group, and it's called the Ornstein-Uhlenbeck process. So if you're familiar with that, well, you're ahead of me. So it's, all right. And I'll come back to that in a moment. Okay. Let me go back to bingo, but instead of starting at 1, 1, I want to look at I start at some point AB, and I want to end up at some point CD. Well, so this is totally general. But what in particular, I want to look at the double limit. I start at some point AA, and I want to end up at NN. And I want to take the double limit as A goes to infinity. So we're avoiding the small order effects. But then, given A, then N goes to infinity. And this could be tightened up. And so then we can ask what the probability is. And then we actually even get the constant. We even get the constant. And the reason is, sorry, again, a LaTeX typo. This is the sum from t equals a to n minus 1. So that n minus 1 should be above. When we look at delta, we can now apply the central limit theorem and get delta. See, we can't do that if the sum is from 1 to n, because x1 itself is a sizable proportion of delta. So in order for the central limit theorem to apply, they don't have to be IID, but no particular variable can be a sizable proportion of the total. And when you start from 1, you're only in a constant regime. So x1, which already is a constant, is a proportion. So like this number beta that we got, we don't know a closed form. Maybe someone here can find one, but some kind of algebraic combinatorics. But we couldn't find a closed form. But when you look at the double limit, now you do have the central limit theorem, and you get that delta is asymptotically normal, and this is the variance. And so the probability of bingo, again, ... means you have to get Subabrata to make it formal for you. You take twice the, where did it go? There it is. Twice the PDF at 0, but now it's given explicitly, again, times the n to the minus alpha. So we get, when we don't start at 1, 1, but start at AA. Actually, a nice story about this, Roberto may remember when we visited Michael Mitzenmacher at Harvard, and he's still there, and I saw him just 2 weeks ago and doing fine. And he and a student, Elena Kosigan, we're doing some data analysis with alpha equals 1.1, and they were running it up to 1 million, and they were discovering that there were a lot of, and they were starting at 1, 1, and they were discovering that often 1 totally dominated, but a fair percentage of the time that wasn't the case, that at 1 million, the two numbers were still roughly the same. And it turned out 1 million, so again, this was a big part, one part of Roberto's thesis, but I think it was really, to me, it was the beginning of the set of problems. 1 million wasn't big enough. 1 million wasn't big enough, that when you look at this with alpha equals 1.1, you have this theorem about total domination, but 1 million isn't big enough for the total domination to actually occur. And so the probability that you don't have total domination up to 1 million balls is not negligible. In the limit, it goes to 0. but it does so like a minus 0.1 power. And 1,000,000 to the minus 0.1 is a big number. Anyway, that was some of the origin of Roberto's thesis. Here is a very interesting question. In fact, let me back up, so I'll just talk about it. Suppose you, well, if you both start with 1,000,000, the chance is 50. Somebody's going to dominate eventually, so the chance is 50-50. Suppose instead of 1,000,000, you had 1,000,003, and the other person had 1,000,000. Well, that 3 isn't going to matter. It's going to have negligible effect. Suppose you had 2,000,000, and the other person had 1,000,000. Well, then that would have an enormous effect. Your probability of being the eventual winner would be very, very close to 1. And so you can ask the question, what is the scaling for when you actually have a significant lead over the other bin? And the answer is that the scaling is by root A. If you have a total of 2A bins, and you have lambda root A more than, so if you have 2 lambda root A more than the other bin, then you've got a significant lead, and the bigger lambda, by lead I mean your chance of total domination. And if lambda is 0.1, it's a relatively small lead, and if lambda is 10, it's an enormous lead. What happens is when you work the probability of bingo, so you can also do this directly for total domination. What happens is if you back up, you get the same CLT, but the lead translates into moving the mean. So what happens here is that this is what it would be if you both went out to infinity, except that you start with a lead because all the steps, the time it takes to go from A minus lambda root A to A plus lambda root A, this one has to take and this one doesn't. And so that moves that over to here, and it's the right scaling, it has an effect. It has an effect. So what happens is that you get the same CLT, but the mean has changed. And when you work it out, you get the same probability, but you get this extra factor because instead it's the PDF, but it's not the PDF at 0. It's the PDF a constant off, depending on what lambda is. And it turns out that's the value. Another way of thinking of this is that if you're ahead by square root of A, you've got a pretty good chance of then later being ahead by 2 square root of A. And of course, these are continuous. And then from 2 square root of A, you've got a really good chance of being ahead by 3 square root of A. And this is the right scaling, and then it just keeps going and going and going. So that's another way of looking at it. So I'll end with just a comment about some of the technical arguments. So this Ornstein-Uhlenbeck process, it's like Brownian motion, except there's a push toward the center. And the push toward the center is proportional to how far off from the center there is. So there's this constant in the Ornstein-Uhlenbeck process, which is how strong is the push. So the push is proportional to how far off you are. And in our case, it's pushing in. And we can, so I have this one derivation, sort of back of the envelope derivation. I love infinitesimals. I think it's really a shame that Leibniz lost the battle there, and we find it difficult to use them because they're extremely useful. So here's a kind of argument using infinitesimals that gives that when you go from time s to time s plus ds, again in this logarithmic time, you change, I think that should be a minus. This should be minus c because you're going back toward the, sorry, so this should be a minus sign. So you've got this push that's pushing you back toward 0. But you also have the Brownian motion, the normal movements. And this is precisely the Ornstein-Uhlenbeck process. And Subhabrata is hard at work at writing this up in a formally correct argument. So I'd like to end with a little bit of poetry due to Paul Erdős. Paul was not known as a poet, but one time he was writing a letter to his longtime collaborator and friend, Vera Schoch. And Paul's letters tended not to be poetry. I mean, I remember I'd get letters, "Dear Joel, let x1, x2, ... xn be," and then, just go on right to the mathematics. And indeed, this letter, I did see the whole letter once, and it is exactly that way. Dear Vera, let, has all this mathematics. And at the very end, though, he had this little postscript with my clumsy translation. It is 6 in the morning, the house is asleep, nice music is playing, I prove and conjecture. So I hope that this week that all of us can prove and conjecture. Muy obrigado.